All right, folks. Today we get to begin our study of related rates. Um, if you have a circle, and the area of the circle is expanding at a rate of 2 inches squared per minute, and we want to find the rate of change of the radius. So how is the radius changing when the radius is actually 10 inches? Let's pretend and put it into context. Maybe you have a puddle on the ground. Maybe something is dripping into it. And the area of this puddle is expanding or changing at a different rate than what the radius is expanding at. So what we want to do first, draw a picture. This doesn't say anything about a puddle. We could use this, or we could just draw a circle. And you don't want to put any quantities in it yet. You just want to, no numbers, that is. You just want to label your circle maybe with just an R for radius. Okay, we're going to label all the quantities given. Let's actually go to C first. Maybe I should have had C as the B. We're going to write a formula needed for a problem. Well, they're discussing the area of the circle. So area of the circle is equal to pi r squared. I want to differentiate the formula with respect to time. Okay, now let's talk about the quantities given, because we are going to have some of them in our formula after we differentiate it. Excuse me. Okay, so what we want to do is, when I say label all the quantities given, give them a label. Tell me R equals 10, for instance. And that's actually the easiest one. Let's go with that first. When the radius equals 10 and our units are inches, we are looking for the rate of change of the radius. Okay, rate of change is slope. Slope is the derivative. So we're looking for the derivative of R with respect to time. These are always going to be, generally speaking, they're going to be with respect to time. So anytime you're working with the related rates, when you're looking for the rate of change of something, that's going to be d over dt of whatever the variable might be, in this case R. Okay, we don't know that. It says to find it, so we'll put a question mark there. Now we know the rate of change of the area, so we'll say dA dt, the area is changing at a rate of, it's expanding, so that means it's going to be positive. If it said that the area of a circle is decreasing, my rate would actually be negative 2 inches squared per minute. So this one is going to be positive 2, and we'll put our units on here because sometimes it does help us in the end. Because units on these problems should always work out if you did it correctly. So it's a good check. Good check on your work. Okay, let's look at D. Differentiate the formula with respect to time. Okay, now this is where we need the chain rule and implicit differentiation, because we're not taking the derivative. We were looking at this before. Taking the derivative of y with respect to x, we get 2. If we had, say, I don't know, let's go with y squared. Then we used implicit differentiation because dy over dx, because this was not the same as this. When we differentiate in related rates, we're always going to be differentiating with respect to time. So we're going to take the derivative of a with respect to time, dA dt, equals, pi is a number, so we're just going to leave it where it is, and we're going to differentiate the r squared. Well, again, the r is not the same as time, what we're differentiating with respect to. So we're going to use our implicit differentiation and the chain rule to do this. If you leave your pi out front, take the derivative of r, bring that 2 down, reduce by 1, you get 2r. But because it's not with respect to r, we put a dr dt next to it. Just like we were putting dy dx's next to things that weren't x, which is what we were taking the derivative with respect to. Okay, once you do that, now you can start putting in your numbers. I know dA dt, and that's going to be 2, so 2 equals, and I'm going to switch this around a little bit. It's going to be, no, actually I don't think I will. I've got r as a nice whole number, so it's going to be pi times, you've got 2 times r10 is 20, dr dt stays dr dt because that's what we're trying to solve for. All right, now I would want to divide both sides by the 20 pi to get rid of it. So that means our answer for dr dt is going to be equal to 2 over 20 is going to reduce to 1 over 10, so 1 over 10 pi. And my units are, this is radius, so it's just going to be inches per, time is on the bottom, and our time is minutes. And I got a positive number, which is good, because I expected the radius to be increasing. Okay, let's work on, I think, number 2. Find the side length of a cube when the rate of change of the side is 12 feet per hour and the volume is expanding at a rate of 42 square feet per hour. All right, let's go ahead and draw our cube. There's a cube. The sides of the cube are all the same, so I'm just going to put S there for side. All right, let's see what we have. It says find the side length. Okay, that's what I'm looking for. It's S. The rate of change of a side, okay, that's going to be ds dt equals 12 feet per hour. Now, let's see. Is it increasing or decreasing here? Would I make it positive or negative? Let's keep reading. And the volume is expanding. This tells me it's going to be plus. Because if the volume is expanding, then the side has to be increasing. So it's going to be positive 12 feet per hour. Volume is expanding at a rate of 42 square feet per hour. So the rate of change of the volume, dV over dt, is equal to positive 42 feet squared per hour. All right, let's write the formula that we need for this problem. Well, we're discussing the cube's volume, so we need the volume of a cube. Volume is going to be equal to length times width times height. They're all the same, so S times S times S is S cubed. Now we want to differentiate the formula with respect to time. So we start with the V. Derivative of V with respect to time equals, now we have an S. Again, though, it's not the same as what we're differentiating with respect to, which is time. So we want to go ahead and differentiate S cubed to be 3S squared, but then next to it we have to write down a ds dt. All right, now we want to substitute the quantities and solve for the variable, which might be a rate of change, it says. And that's because I wanted you to understand that sometimes, like up here in number 1, our variable is actually a rate of change there, drdt. Okay, this time it is not, however. We are looking for s. All right, dv dt is going to be equal to 42. And then 3 times s we're looking for. So we'll leave it as s squared. And then ds dt, we're going to multiply by 12. Okay, so that's going to give me 36s squared. Divide by 36. So we have s squared equals, all right, now we want to grab the calculator because not only are we going to have, we could reduce that fraction, but we're going to have to take the square root of it. So we want to go ahead and punch it in. So 42 divided by 36 gives me 1.16 repeating, and I'm going to take the square root of that answer. So second square root of the answer, and we get plus and minus 1.08. Now, we could get a possible plus and minus, but we know that, excuse me, I'm going to get rid of that little 2. Hold on just a second. Got rid of too much. Okay. So let's see, 36, put that back there. All right. Generally speaking, when we take a square root, we get plus and minus. But in this case, if everything is expanding, then I'm going to choose the positive. So the answer is positive 1.08, and what are our units here? Feet. Okay, flip it over and try numbers 3 and 4. Decreasing. I'll give you a tip on this one. The volume is decreasing at a rate of 5. That means that the volume with respect to time equals negative 5 centimeters cubed per second. So you want to really pay attention to what should be positive and what should be negative as far as rates go.